Hi, welcome back. In the previous section, we talked about how to linearize data or approximate. I don't know why I'm stuttering on that word. Data using a linear function. So, and in the beginning of that slide, or beginning of the last presentation, we went through an example with a cantilever beam, and we plotted out the data. And without having kind of any talking about how to identify functions, we all kind of immediately went to that it was a linear function. And so in this little section, we basically are going to talk about three different types of functions that are commonly used to describe physical phenomena. And the linear function is one of them. Before we go too far into identifying functions, one of the things I wanted to put in here was just kind of a reminder about the properties of logarithmic functions. And I didn't want to do anything more than just put these up here so they're in your notes, and just kind of a reminder of how to manipulate and separate out if you have a log of two numbers multiplied together or two terms multiplied together, like this first section here. Oh, I just erased. Or if you have a logarithmic of something to the power of m, you can pull that m out in front of it and separate it out. So just kind of a quick reminder of these properties, and as we go forward, we'll be kind of taking advantage of those properties. So we've already kind of talked about the linear function, but just so we kind of put these all together, the linear function has properties, or can be modeled by y equals mx plus b. And we know that, just by looking at this, but also from our previous studies, that the y, when x is equal to 0, is equal to b. So the y-intercept is b, and the slope of the line is equal to m. The power function can be represented by y, and let's just put this little of x in here, equals b times x to the m. And depending on what the value of m is, that kind of dictates whether or not this process goes to 0, or whether or not it goes to infinity at a value of x equals to 0. So basically we have if, I'm going to pause it for just a So the power function, basically, just what I said was, if the m value is greater than or equal to 0, it's going to be 0 at x equals 0. And if the m value is actually less than 0, then it would go to infinity. And that's kind of logical, I think. So the exponential function, y of x equals b times 10 to the mx. And it has an equivalent form of b e to the mx. And those are not actually equal to one another, but an exponential can be modeled in either form. So for both of these cases, the 0, y 0 is equal to b. Now, if we go back and look at these, if we plot the linear function, if we just plot that on kind of what you'd call a normal axis, or the book calls it rectilinear, it forms a straight line. And that's just kind of obvious, I think. Now, with a power function, if we plot this on a log-log axis, you end up with a straight line. So we'll put this in here, that log-log axis yields a straight line. But if we go back to the equation, and let's say if we just take the log of both sides, so we end up with the log of y to the x, and set it equal over here, we end up with log of b plus m times the log of x. So if we go look at this, we know then the y-intercept is equal to log of b, and the slope is equal to m. And if we just look at this equation and compare it back to our y equals mx plus b form, you can see the same relationships where this log of b corresponds to this term. The m still corresponds to this term, where your x term, you're actually plotting it against a log. So I'm not sure this has gotten very messy all of a sudden, but hopefully you can see what I'm trying to get at. The exponential function, if you plot this against a semi-log axis where the y-axis is logarithmic, you would get a straight line. So semi-log, and I'm just going to put a little y here so you know that it has to be the y-axis that's plotted on the logarithmic. That would give you the straight line in this case. And once again, if we take the log of both sides, you end up with log of y is equal to log of b and plus mx, since that is to the power. And so if you look back at those properties that we went back on the other side, you should be able to see this equation. So once again, your slope is m and your y-intercept. When you plot it on the the semi-log plot, the y-axis is going to be log of b. If you plot it on normal plot, the y-axis would just be equal to b. So it just depends on which plot you're using. So that's kind of it looks much messier than I thought it was going to, but the idea is there's 3 different types of functions, and it's important to kind of understand what the properties of those are. And as we start talking about things like this, depending on what the m value is for a power function and so on, that as we try to identify these parameters, if we kind of know in the back of our mind that a power function exhibits these types of behaviors, it becomes a lot easier to identify those. So when we try to identify one of these steps, certainly in the previous lesson when we went through that example with the cantilever beam, we looked at, we plotted out the data and it was kind of like, we knew right away what it was. As we get more complex systems and a little bit more, well, just more complex, we're going to find that maybe it's not quite as trivial to come up with that. So one of the big assumptions we're making in putting these kind of like 4 steps for identifying the type of function, the assumption we're making is that the data can actually be represented by a linear, a power, or an exponential function. And that's a pretty good assumption, or a pretty safe assumption when we're talking about physical systems. Beyond that, there are certainly times when this doesn't work. However, for the purposes of this class and for most engineering systems that you're looking at, this type of a strategy is relatively effective. So the first step I've listed here, and I've taken these out of the book. I changed the last couple a little bit around because I thought the book was a little bit weird. You end up doing the same thing, but so the first step is the same as the book, and that's look at the data near the origin. So we know that the exponential is never going to pass through the origin. So if it's an exponential, if it doesn't pass through the origin, then it could be an exponential function. If it is passing through the origin, then we know that it's not an exponential. So we can kind of rule that out right off the bat. Now, if for some reason we know that b is equal to 0, then it could be a linear, and it also could be a power function if the m value is greater than 0. So I'm going to pause here and write these 3 kind of ifs or things down before we move on. So, all right. So I just wrote down kind of what I had just said. For each of the 3 functions, it kind of has a characteristic behavior. And basically, in going through these steps, we're looking to either eliminate or affirm that it could be a specific type of function. So once you get through this first step of looking at the data near the origin, the next thing that you would do is plot the data just using rectilinear scales. So rectilinear is just a fancy word